Yeah, it's live, Ines. You can start.
All right. Welcome everyone to this series of talks of the QCTalks. Today we have the pleasure of having with us Dr. Sofia Vallecorsa. She works for CERN, and today she has this very beautiful background that everyone can see. Sofia has been working with quantum machine learning, high energy physics, and we are looking forward to see what she has to talk to us. Thank you very much, Sofia. It's up to you now.
Thanks, and thanks for having me here. So I'm very happy to be here and talk to you about the research we started doing at CERN on quantum machine learning. I have the tendency to run out of time. So what I did in this case was to do a pre-selection of what I want to talk to you about and allowing for some bonus material, additional material in case we get time at the end. So here's the outline of my talk. I will start with a brief introduction about CERN and the QTI, so the Quantum Technology Initiative, and some general concepts about quantum machine learning. It's not really going to be a detailed explanation of what quantum machine learning is, but this is really more meant to focus on what are the challenges and what are the topics that are important if we want to create a realistic application. And then I will go on with a few examples we've been working on at CERN, and I want to stress that those are really examples. This is by any means, it's not a complete list of what's going on at CERN and within the high energy physics community, but I had to make choices. And so I chose work we've been doing directly at CERN Open Lab. So let me start just with the usual introduction about CERN. You probably know us. This is our lab. It was founded in the 50s. And it's an international organization which is at the border between Switzerland and France. It's today one of the biggest experimental facilities worldwide, and also from the point of view of both from the point of view of the engineering facilities, but also in terms of number of people and scientists that work there. You can see some numbers here. You can see that we receive funding from a lot of member states, but there are a lot of other states that can participate in our scientific program within different categories with different status. I will not go into the detail of what we do at CERN. I'm assuming you all know or have an idea, or we know to find out. What I wanted to stress is the initiative on quantum technologies that we started about a year ago. This year, just a few weeks ago, we presented our QTI roadmap to the CERN Council. This was a big step for us. We've highlighted what will be the plan for the next few years regarding quantum technologies in general. So you can see here the two main things that make the roadmap. The general strategy and what we want to focus on as long-term goals, and the way we want to implement this. So again, let me just say that the idea of the QTI was really about trying to give a common background, a common framework for all the studies that started within the community concerning different topics. Of course, the focus is about assessing the impact of those technologies for our research. Time scale is, of course, our luminosity LHC, which is right now our, the biggest next program, but also beyond that. And of course, we are very well aware that it is necessary to start building knowledge well ahead of time, because these technologies require a very different approach to solving science problems, problems in general. And this can be achieved effectively only through by slowly building the capabilities and the capacity to do this. And to do so, we started, we defined a set of concrete R&D objectives. Those are, and we'll show you right away what the main areas are. but also investing in creating opportunities for education and training in collaboration with external institutes and with the community at large. So those are the main areas that the QTI covers. So computing, of course, so this is the part that I work on. And you will hear today about, but the QTI at CERN actually includes a lot more than that. Quantum sensing, for example. So the idea of studying quantum technologies for detector applications, low energy measurements, nanotechnologies, but also designing the future of high energy physics detectors. There is also an area that is more related to communications, OpenQKD, we have a node at CERN, but also the idea longer term of quantum internet and theory. So direct application of quantum technologies to quantum field theories, the lattice QCD, direct simulations of quantum systems in general. So why quantum computing? This is a question we get often. I think it's natural. High energy physics in general, it's a natural application of quantum computing. We do know, we do analyze classical data because usually this is usually the output of a detector of a measurement. So it is classical in nature, but it is generated by quantum processes. So the idea would be to test or to understand to which extent quantum computing can improve the way we can describe, we can understand the underlying correlations that are generated by quantum effect, but are measured as classical quantities. Okay, so this is the general idea. Of course, we can go, more specifics into quantum machine learning. Now, I would like to. So I have prepared really a talk about quantum machine learning. This is for now the core of our applications, but it's not the only field we are interested, or the only, let's say, kind of algorithms, the only approach we are interested in, of course. But let's focus on quantum machine learning just for the next half hour, 40 minutes. I would like to stress again. So when we talk about quantum machine learning, there are two main views that we might be using. One is the idea of using machine learning to discover new quantum algorithms, or in general to improve quantum algorithms or to improve quantum circuits. And this is a very interesting and lively field, research field. This is not, however, what I will be talking about here. What I will talk about here is the idea of using quantum computers to accelerate or improve, and you'll hear plenty about this, machine learning and deep learning models, either at the training level or inference, or overall improving their general performance. And the idea behind is the fact that quantum circuits indeed are differentiable. So basically, we can think of them as neural net. We can easily interpret them, and we see what easily actually mean as neural network. But the bottom line is that they can be trained, minimizing a cost function. Of course, you are probably aware of the immediate difficulties, let's say, of wanting to bring, of trying to bring a quantum, a machine learning, deep learning approach. And you'll forgive me, but I will actually use the two interchangeably here. Okay, machine learning, deep learning. I'm not making a real difference. It's not relevant for this discussion. What I just want to stress is the idea of trainable algorithms that require a large amount of data to work. Now, this, of course, is already an aspect that is, that can limit or in any case be hinder somehow the use of quantum circuits. Okay, so the idea that today it is not so easy to use quantum computers to process large amounts of data. Okay, so this is something that needs to be taken into account. So what does this mean in practice? What does implementing a quantum machine learning algorithm mean in practice? So of course, yes, that is the whole discussion I just started about data. you can think of using quantum machine learning algorithms on quantum data or on classical data. Most of the applications that exist today, but not all actually, but most of them use focus on classical data. This is also all the examples that you see today are related to, are built this way. So then, of course, it is important to stress that the way we represent our classical data in quantum circuits is critical in order to improve the performance of our models. There are other aspects that are important if we want to, reproduce the behavior of classical deep learning into a quantum circuit, and it is related to the way we introduce non-linearities in quantum circuits. Those are all unitary gates in quantum circuits are all unitary matrices. How do we then introduce non-linearity? There are specific approaches that can be used. You could think of approximating your nonlinear activation functions into a polynomial, for example. You could think of using kernel methods and somehow work around the problem of nonlinear activation functions. And I will show you, we will talk about this. And then, of course, there is the problem of convergence. Now, convergence of those models is already something that is very, that can be very difficult in the classical setup. There is the famous problem of barren plateaus. This is very well-known behavior by which at some point you can, depending on the structure of your network, if it becomes very deep, for example, you can end up into a region of your phase space in which the gradients become so small that optimization is not possible anymore. You cannot move around. You will not improve on the convergence of your network. Now, it has been observed already a few years ago, and one of the first papers, I linked it here, that discussed this problem was published by Google some years ago now, and they really showed or linked the problem of barren plateaus to the size of the quantum circuits that are used to represent our models. Together with that, with this observation, there have been, of course, also a lot. There has been a lot of studies in trying to, again, find workarounds, find solutions to this. There are options, in particular, and here I quote another example, and I just realized I didn't correctly add the reference. I will do that when I share the slide. I'll do that later. But there are, for example, specific architectures that can be used to reduce the problem related to, vanishing gradients, and the three tensor networks are an example of this. And also those plots are taken from some recent work. This was published a couple of years ago. So the other thing I wanted to clarify or at least touch on before going into the example is the definition of quantum advantage for quantum machine learning. When we are talking about other algorithms, we are usually talking about complexity. So we try and understand whether a quantum algorithm could solve a problem that is too complex to be solved classically, or whether it can do it faster. That is not necessarily the only kind of advantage that you can look for when you build a quantum machine learning models. So of course, yes, it's one of the ways, but we are interested also in understanding whether sample complexity exists. So the idea, for example, of being able to train a quantum model using effectively a training set that is smaller than what be needed for the corresponding classical model. And then there is the whole discussion about representation of power. Can we assume, or can we, I think, prove that a quantum circuit, so a network built using quantum states, will have the ability to learn probability distributions that are more complex with respect to what the corresponding classical algorithm could do? So is this something that is reasonable? Is this something we can prove? Is this something we observe? And so that is a different way of advantage, right? Then, of course, there is the discussion about practical implementation. When we're talking about advantage in general, theoretical terms, that is certainly important, especially over a long-term kind of perspective. But of course, practical implementation can then change entirely, can change the situation entirely, okay? So I talked, for example, about speed up. If our approach to data embedding, for example, it's slow, the practical implementation of a very fast algorithm is in any case going to be at a disadvantage with respect to classical models. So from a realistic application perspective, this is something we should take into account. And there are, concerning, let's say, this near-term, the use of near-term devices, there are, of course, concerns, let's say, not concerns, but there are effects that are related to the choice of the algorithms, but also engineering problems related to the hardware itself and how the hardware is integrated in our currently in our classical computing models. So basically the idea, if you want, the idea of our studies so far has been really trying and create control environment, trying to choose problems that we actually know how to solve classically. That we know very well how they behave, that we know of which we know all the details of the training data sets, so of the general environment, and then design or study how quantum algorithms perform. Okay, and so the idea is really characterize their behavior and try to do some sort of systematic study in order to understand advantages or challenges. And very last thing, I wanted to stress again that for today there are basically two main ideas behind quantum machine learning implementations, and depending on how familiar or you are with them, with those two ideas in the classical world. So we're talking about, in the classical world, we're talking about neural networks versus kernel methods. You might find advantages and disadvantages in using a similar approach in the quantum in the quantum world. Of course, there are differences with respect to to the classical implementations, and there are aspects that need to be taken into account. In particular, recently, I would say that whereby recently I mean couple of years, kernel methods. So the implementation of quantum-based kernel methods have really brought back this approach in full force. The reason behind this is the fact that because of the way we design embedding to represent our classical data in quantum states, we automatically somehow are generating, are defining kernels that can be used to set up optimization problems. And in this case, the big advantage with respect to a typical neural network approach is that we are designing a convex optimization problem, a problem for which we know that there is only one minimum that we are going to find, basically, that we are sure we are going to find. Of course, practical problems aside. Okay, so this is a big advantage with respect to the typical neural network approach, which translates in the quantum world with variational algorithms. Okay, the disadvantage in this case is that, of course, the computation is related to the size of the data set, scales with the size of the data set that you are analyzing. Okay, in particular with the data set, the number of pairs you can build within your data set. As far as variational algorithms are concerned, those are used well beyond the field of quantum machine learning. So this is a very generic approach that has been proven to work in many different applications, from quantum chemistry to financial applications. The interpretation of variational algorithms as a machine learning method is, if you want, straightforward. This is represented here. The core of those algorithms is the fact that you basically you can represent your variational algorithm as a set of I don't know if you see my pointer, actually didn't ask. Yeah, okay. So a set of circuits that are run on your initial state. In this specific sketch here, you see an initializer a circuit that is used to embed the input data, and then the circuit that represents a specific task you want to solve. There is a parametric circuit, and in which the parameters are optimized during training. Okay. So the next step, of course, is the output of the circuit is measured, and it's used to build a loss function in exactly the same way you would do this in a classical model. The loss function is then optimized. So gradients are calculated, updates can be calculated and be applied, are calculated classically, and can be applied back to the variational circuit. And this is a process that is repeated throughout the whole training data set in exactly the same way you would in a classical setup. Now, of course, also, again, this is a very versatile, flexible kind of model. There are a lot of things that can be improved, can be changed. Also, the data embedding circuits, for example, can be learned. By default, everybody uses gradient-free methods that are actually, stochastic gradient-based methods, such as stochastic gradient descent. But in fact, it's an approach that is suitable also to use gradient-free methods and skip right away the problem of vanishing gradients, for example. You could think of doing this using QAOA kind of approach or evolutionary algorithms. Okay, I will not really go into the discussion about what would be most suitable in terms of integrating quantum hardware with classical computing. Of course, in a variational algorithm, this is a very important part. The trend today seems to be to design quantum chips as sort of accelerators to which offload parts of the algorithms that are optimized specifically to that. We don't know if that is going to be the long-term solution. Now, here is a list of some of the work I wanted to show to you. So you see those are applications. If we go through them, I've highlighted here the application. We've been studying different tasks within the typical data processing chain. Okay, so we are talking about, for example, simulation. We're talking about particle trajectory reconstruction. This would map to a typical pattern recognition. Pattern recognition problem. Higgs boson identification. This is a typical binary classification problem. Study of the embedding, anomaly detection. Also, this is a very general, if you want, technique and in class of problems. And optimizations. In this case, what I really mean here is setting up reinforcement learning kind of environment and framework to optimize this particular application is dedicated to optimize beam in accelerators. Okay. Now all of this work is done actually at CERN in collaboration with external institutes. Okay, so it's actually pretty. Those are all very nice examples of collaborations, both with academic institutes and industry. So let me start with our simulation problem. So we studied the problem of detector simulation, and in particular, the idea of implementing generative models in as quantum or hybrid architectures. Now, we focused on a specific approach, is the generative adversarial network approach, which is also one of the models, the classical models we developed for our independently, okay, for our detector simulation studies. And this is actually one of the models that are the most, I would say, promising and that are being heavily studied by the community as a possible replacement for Monte Carlo simulations, Monte Carlo-based simulations, which are very, very expensive in terms of computing resources. One of the problems with respect to generative models, so what does a generative model do? The idea is that A generative model is trained on some sample training data, and it learns the underlying probability distribution function. And once it is trained, it can be used to sample new events that belong to the same population, and therefore exhibit all the typical features that you'd expect to see in the original data. Okay, so this is the reason why we can use them as replacements for Monte Carlo. There's many of them. I think they are among the most studied models, at least now that deep learning is again in full force. The problem that we encounter when we try to apply those models to scientific simulation is really the fact that we need to evaluate what is the size of the support space that the generative model learns. So what is the coverage that indeed the generative model is capable of reproducing of the original phase space? Okay, because if the generative model is not well trained, then we risk biasing our simulations by excluding blindly, basically, regions that in the phase space that might be interesting. And we did observe actually that this might be the case for some of the applications we developed classically. So for us, this was one of the first reasons to try and implement this as a quantum circuit. Just briefly, you probably heard about GANs already a lot, so I will not spend time on this. They're a very popular model. The idea behind is that the training happens through what's called the adversarial process. A generator network, which is the one that has to learn this probability distribution function, and indeed is the one that then is used to sample new events, is trained against a discriminator network that somehow supervises the learning of the generator network. Okay, so this is very, if you want, it is a relatively unstable training point, because what you are actually searching is not a minimum, but a saddle point in your phase space, and makes it less convergence more difficult. But once it's reached, the model is very sharp. You can get samples that have very high quality. So in the quantum world as well, exist a few prototypes, GAN prototypes that have been proposed. We used one that was initially proposed some years ago by IBM. This is a hybrid model which trains a quantum generator against a classical discriminator. And we used it to learn energy distributions of single particles that cross a detector. Basically, what you would see in a one-dimensional setup would be, you can imagine a particle that enters the detector this direction, deposits a certain amount of energy along the detector depth until basically the end. And this is the typical shape you would expect. And so this is in one dimension, and you can see something similar if you imagine to plot it in a two-dimensional scale, in which you have the transverse dimensions that's orthogonal to the incoming particle trajectory, and again the calorimeter, the detector depth. So we built a model using just 3 qubits that could reproduce very well the average energy profile in one dimension, and then we increased to using 6 qubits to reproduce the two-dimensional distributions, and then you can see results here. Those were obtained with a relatively simple circuit that is based on rotational Y rotation gate. Okay, we studied what happens. So that was noiseless, ideal simulation setup. We studied what happened when we actually try to run this model on quantum circuits. So this is still simulation, but we did use the realistic noise models. What we wanted to understand was to see whether how noise affects training of those models, if error mitigation techniques are needed, and or whether a GAN model as a neural network model in general would learn how to model the noise itself and automatically compensate for this. So we started by simplifying the noise models. So we focused initially on readout errors with a certain fixed probability. You see plots here that were built simulating noise at 1% error rate, readout error rate. And we studied how this noise affects the convergence, so loss functions. The final result here is the original and the simulated distribution, and well, we try to quantify this, measuring the relative entropy between the two distributions. So we found out basically that for such a relatively small but reasonable amount of readout error, the performance of the networks are actually better. And we don't need error mitigation because we can reobserve or reobtain convergence by simply changing our training hyperparameters. We actually scanned, that was just an example, we scanned different amounts of increasing error probabilities, and we found out that indeed this, again, this is preliminary. So if you notice, we still have a rather large uncertainties on those numbers, so please take them with some care. But there seemed to be a trend up to a certain amount, relatively small amount of noise. We can just simply reabsorb, so the network learns the effect of the noise and compensates for that. We can just rearrange or retune our hyperparameters and obtain very good results. After a certain point, but this is about a probability error of 10%, which is very, very big, okay, kind of unrealistic in today's hardware. But nevertheless, up to that point, then error mitigation becomes important. We also studied full noise simulation. So together with readout noise, there are certain kinds of errors that can happen during runtime at the gate level, at the single qubit and gate level, and they are always specified, calibrated in the near-term hardware. Those are and accounted for. So we used one of those models, specific of this chip, this IBM chip, and we observed the behavior of our network, including therefore both readout and gate error noise. And we found out that the convergence is actually improved with respect to the noiseless simulation. And this is actually not, if you think about it, it's really not surprising, in the sense that even in the classical world, so in classical deep learning, it is well known that introducing a certain amount of stochasticity in your data can actually improve. So a certain amount of noise in your training dataset can actually improve the final performance at convergence. Okay, so this was a very interesting result to see it also in this setup. We did test also or simulate another, let's say, behavior. We wanted to test the stability of a trained model. Okay, so in a typical application, what would happen is that we would train the model and then ideally use it many times. So what happens is the noise level on the hardware actually changes over time. Okay, we know that it can fluctuate. How robust our models would be in this case. So we loaded the pre-trained models and studied the stability of the inference process. Basically, what you see here is how the relative entropy changes with respect to increasing noise levels of different kinds. Okay, either readout or gate level noise, or both at the same time. And basically, we found out that we can get stable performance up to about a few percent error rate for both the readout and gate level, which is which is reasonable if you think of how those devices behave today. Okay, I will change topic now and go quickly through quantum classifiers. I will show you two examples. One is a set of classifiers we defined for track reconstruction problem. Now, this is a very, very complex problem, especially if you're looking into high luminosity LHC, when the complexity of the events of the collisions that will be generated by the collisions will be much, much higher in terms of number of particles, but also in terms of granularity of our detectors, okay, which will be higher with a larger number of sensors. So the idea of particle tracking is really trying to figure out which the detector hits, so which detector signals are actually associated to the correct particle, okay, and then use this information to gather physics features out of it. Measure the energy of the particle, the momentum of the particle, and so on and so forth. So from the classical point of view, we have a very interesting project that has been already successful for many years, which is the ExaTrack X project, which developed a graph neural network to do this. In fact, the ExaTrack GNN uses a set of networks, a chain of networks that, let me go back just a sec, that basically classify the quality of each one of the hits, of the detector hits, and of the segments that connect them, okay, as choosing the ones that are actually relevant for the final trajectory. So those are basically called the node network and the edge network. So what we did was to replace in the exact same architecture the edge network and the node network. So again, two different kind of two classifiers basically, with hybrid networks consisting of an initial set of fully connected layers that we use to reduce the dimensionality of our input, and then a quantum circuit. And we tested many different quantum circuits. Here you see examples for hierarchical classifiers. So this is a class of circuits that uses specific patterns, specific entanglement patterns among the qubits. And in the plot here, you see how the performance of the networks, the quantum networks, are all the orange points, compares to typical classical solutions. Okay, so you see that, well, especially for the AUC scale is what you see here. It's actually very much zoomed in. So you can see that they can get very close to the classical cases for a small number of parameters. Increasing the number of parameters increases the performance of the classical models. We did some more quantum circuit systematics. We studied how, I will not go into the details here. We basically compared how different entanglement patterns affect the performance of our networks. We studied how, for example, the embedding we choose for our data. We studied how the affects the performance, the number of layers, the number of iterations that we need to train for, or the size, the depth, basically, of our circuit. The other classification example I wanted to show you is a binary classification problem. So we focus on a specific Higgs channel. This is actually a favorite of our community. We are all looking at identifying Higgs signals with respect to background. Different Higgs decay, but this is a very, very common use case. But we used it as a together with the classical models that are used to do the analysis, so to do the classification in the standard setup as our baseline, as the use case and baseline. So this is a rather complicated Higgs channel. I don't know how familiar you are with Feynman diagrams. It's a favorite of particle physicists. The idea here is just to realize that we are looking for this Higgs particle here that is created by the interactions of the two gluons and that decays into two B quarks. Okay. Bottom line is that together with the Higgs top quarks are generated, and at the end of the chain, we get a very complex event with a lot of particles. Okay. So at a very high level, this kind of event can be or is studied usually measuring a total of 67 features. And in the classical analysis, those features are fed through BDTs, for example, or deep neural network. And then there is a certain accuracy, classification accuracy that is achieved. That is of the order of 70%. In the best case, more complex models, this actually went up to about 80% today. But we are talking about interaction network and very complex training. So we use this use case to study the effect of quantum support vector machines and quantum classifiers. So compared what I said about at the beginning about comparing kernel methods and neural networks. And we found that in this case, the two have similar power with a slightly stronger, better accuracy achieved in the classifier. I will show you just in a second. I just wanted to mention here, the plots that you see here are ROC curves, and that show so the background versus signal efficiency in the two cases, and compare quantum SVM to classical SVM for two different sets of qubits, and therefore two different sets of initial features. So for us, what was really interesting about this project was also understanding how the initial classical feature extraction step affects the final performance. You can see we can look through the numbers. I don't know if you can read them on the screen, but we are ranging between 62 to 67% AUC. In the case of the quantum classifiers, instead, we built a network. Again, this is a hybrid setup in which there is an initial step that relies on fully connected layers that does the dimensionality reduction step. There is an embedding that uses the so-called ZZ feature map, which is used here. Basically, is a feature map that is based on Z rotational gates. And simple variational form with data reuploading. So data reuploading is the idea of embedding a certain portion of your data, certain part of your data in your quantum circuit, running your classifier circuit, reuploading new data, and rerunning your quantum circuit in a chain, basically. So this is the advantage of allowing analysis of larger data set. The obvious disadvantage is that you end up with very deep circuits. Okay, so let's say, I would say a trade-off is needed, at least at this level, taking into account the status of the current hardware. What really made a difference in the case of the VQC, you can see that we achieve here AUC, which are very close to the classical case with almost 70% AUC. And it's the fact that we train together the initial feature reduction step and the classical, and the quantum classifier as a overall, as a unique hybrid trainable circuit. Okay, so this brings me to the end. I actually don't want to spend time on the summary. I prefer to take questions. I can just say that I chose those examples to highlight really a few points, okay, which I think are very important and need actually further study and further analysis in order to really try and divide and design algorithms that are useful for real problem on near-term devices. So thanks.
Thank you very much, Sofia. Pedro has raised his hand.
Okay, well, thank you very much. We cannot applaud because maybe it's a little bit strange, but it's fine. Thank you for the presentation. I mean, I don't have my broad knowledge of quantum is not that great, but at least I got a little bit of an idea that you're using quantum technologies to tackle a set of problems, a very wide range of problems. So that was good. So my question maybe is a little bit more, shows a little bit my ignorance. At the beginning, you mentioned these two types of methods, the variational method, was it? And the kernel methods. So some time ago, I worked on a software project in the GAN4 software, and essentially we're doing things like approximation of hadronic cross sections.
Yes.
So, and my notion at the time was that a lot of these algorithms in high energy physics are probabilistic in nature. So how are you using mostly this encoding of probability of quantum states? Is in the data, in the learning process? So that's why, or in both? I mean, well, how do you see, because it seems to be that this is a great match, because you have now this probabilistic distribution of states, of quantum states. And so I'm wondering if you basically see more focus on one approach, that is capture the probability of the whole events in the states, or in the probability, or the more probabilistic classifier. I don't know which one makes more sense, or both. I don't know.
Yeah, exactly. So my answer would be both, actually, because we are seeing now that so of course the easiest, you know, the first test we all do, the easy thing you can try is really to apply this at the classifier level. Okay, so you try to design the best classifier possible, and then measure or optimize it. But what we actually saw is that the way if we take this probabilistic interpretation into account already at the step in which we design the way we represent our classical data in quantum state, this really makes a difference. Okay. There is this is something that well, it's actually well known in other applications too. So this has been shown already to work in quantum chemistry. But we've seen it, let's say, in our, you know, we are relatively new to the field too, with respect to applications in quantum chemistry that have been around already for a longer time. But we saw this. So, so if we take into account the topology of, for example, let me get back to this. No, actually, it's the back. So if we take into account the topology of an event, in the way we design our initial input circuit, this is certainly going to help us. Okay, and this is even more true when we try to do direct simulation of a quantum system. So you mentioned GAN4 and the evaluation of cross sections.
Correct.
So in putting QML aside, if we wanted to use a quantum circuit to simulate a physics process, what we should try to do is to write the Hamiltonian and try to represent the Hamiltonian in our quantum state. So use the quantum states to represent the Hamiltonian behavior, right? Basically. Gotcha. So that's exactly what you said.
Okay. All right. Thank you very much.
Yeah.
Thank you, Sofia. I don't know, I have two questions to you that I put in chat, but I wanted to know if someone else has some other question for Sofia. Rui, are you there? Do you have any questions from people from YouTube? I don't know if they can interact.
Yeah, no questions there.
Okay, right. Sofia, I have two questions for you. One of them, I may be confusing here because, as Pedro said, I don't have a very broad knowledge about quantum computing, although I don't know how I managed to supervise a PhD student in quantum computing, but anyway. My question is, there are these two classes of architectures. One of them is circuit-based and the other one is adiabatic. And it seems to me that some of the problems that you showed here fit better the adiabatic model that is more for optimization than the circuit-based. So why are you working with circuit-based for some of these problems? Yeah,
so I showed you examples that are circuit-based, but we are actually working also on the adiabatic approach. And the idea, so in the case of the adiabatic approach, the easiest way to use this is to be able to represent the model that you have at hand as a Ising model. Okay, so depending on how easily this is possible, then I would say you would go one direction or the other. Now, a lot of those models that are like quantum SDN or even other more models that are closer to the standard neural network approach are being trained using quantum annealers, for example, because the cost function basically is mapped we can build the cost function, map it to Ising model, and then use the annealer as the optimizer, basically. And this is indeed very can be very powerful, and we do use it. In fact, the reinforcement learning example that I didn't show you does that. And we do see, so basically the idea of this reinforcement learning problem, this is, you probably are familiar with that. We translate the Q learning approach, okay? So instead of using a classical neural network to evaluate the Q function, we use a Boltzmann machine. And the Boltzmann machine, for the Boltzmann machine, we define the Q value as the effective, the free energy, basically. And once we do that, then we can use a quantum annealer to find the state with the configuration with the lowest possible energy. Okay, in this case, well, we change the sign and then it becomes the maximum Q. Fine, but that's the reason. And this works very well. So we managed, using the annealer, we managed to train. I don't go into the details of the example, but this we managed to train an agent in less than 3 times the number of training interaction that we need in the classical case. Okay, so this is actually an approach that is being used now as well.
Yeah, that's very interesting. Actually, you could give another talk to us with more details about some of these applications. I mean, one of them, maybe. I don't know if all the others agree, but I mean, this is a very interesting subject.
Yeah, but actually, one of the first application of QML to our, to physics is a work that has been published on Nature. I can share the references, and that used indeed the quantum annealer to train a classifier. Okay, so and this was published in 2017 by a group at Caltech, and it was really the first application of quantum machine learning to physics, to high energy physics. So it is indeed a very powerful approach.
All right. The second thing that I wanted to ask you was about the time, execution time, or at least complexity. I know that we cannot compare directly the classical times with the quantum times, but in the beginning you said that one of the advantages of using quantum machines is to reduce time and also dimensionality, right? But time is something that puzzles me because some experiments that we have been doing with quantum machines take longer than the classical solutions. So this is a bit disappointing.
Yes, no, I agree.
5 minutes, nothing will be done.
I'm sorry. There was another.
Yeah, someone was saying. Pedro was saying something. No, I think
sorry.
No, okay, no. So yeah, indeed, this is a tricky question in the sense that in most cases, so we didn't study, algorithmic complexity in any of the applications you saw. Okay, so we searched for a different kind of advantage here. So it wasn't really related to speed up in terms of time, but all the work and all the studies that deal with this are usually discussing theoretical complexity. Okay, so how using a quantum algorithm, designing from scratch, or maybe using, I don't know, a Grover algorithm with respect to a standard search can reduce the complexity, the theoretical complexity, and therefore bring advantage in terms of time. Now, that is different than actually making the measurement on a real hardware. Okay, so unfortunately, this is not necessarily something that then is always possible to, to measure and to observe. Mm-hmm. And I think this is something to, now, I didn't show you any benchmark on hardware. Everything you saw here, even, the GAN models were all run with simulators. Mm-hmm. But the first test that we have showed that it is indeed not faster, okay? That is a specific case because there is a lot of interaction that is going on because of the adversarial setup between the generator and another classical network. So we can't really compare. But for this kind of application, we didn't really see a speed up in terms of time. Okay, we saw that we can run for a smaller number of epochs. We saw that we can run on a smaller data set. Not necessarily accelerating the calculations themselves. Let's say.
Yeah, this is a bit disappointing. But anyway, because I understand that it's also very difficult to take the proper to produce a proper timing for these machines. I mean, to know exactly what's the time that the process is taking.
Well,
anyway.
But nowadays, for example, if you use, it depends on the specific hardware, okay, and it depends on what is the framework that you use to load to run on it. But for example, for the IBM, it's just an example. What you can do is to analyze and measure every time you submit your work. The time it takes to do, transpilation, loading the circuit, and then you do have indeed some estimate of what is the time that the quantum chip is taking to, takes to make the computation. But it's still it's still an overall number that you get. Yeah.
Okay, thank you. Pedro has his.
Yeah, I had another question. If there's nobody else with questions, I want to give opportunity to other people to ask the question. No, there's nobody else. So my question, this may be a little bit of misperception on my side, but some of the interesting events in high energy physics maybe do not correspond to a minimization of anything, I don't know, in terms of energy. So that basically goes to this question, I mean, is the Ising model where you're looking for an adiabatic approach in which you want to minimize some notion of energy, is it really a good match, or are you minimizing something else, which is the model that explains these events? So I might be missing something here. Right?
No. So it's different things. So you can do different things. Okay, there are problems that you can map directly to Ising models, and then you really are interested in finding the lowest energy state that is fine. Right. Then there are cases in which, for example, many of those quantum machine learning applications that are solved this way, where is the loss function that is mapped geometrically, if you want, without really, any physics interpretation. To such a Hamiltonian, so that then the standard machinery can be applied. And then there are problems that indeed don't map so easily. Right. And then for those, yeah.
Okay, good. Thank you.
Sure.
All right. So I think does anyone have any other questions? Otherwise, I think it's time to finish. And Sofia, I think, is there anyone else that wants to ask some question? No?
No, yeah, I think we're good.
Not. Yep, okay. So I think we agreed as well. No one else said anything, but I think Sofia is going to be invited again.
Well, it would be a pleasure. I hope I'll be able to travel. That would be nicer.
Yeah, that would be good.
Possible.
Yeah.
Hopefully,
we would like to have an in-person event at a given point in time. So hopefully, with your connection to Phil, it's maybe even a good thing, a good match, so to speak. Okay, thank you, Sofia, for your.
All right.
Thanks.